Hello everybody, basically Mr. Hinnon here. I'm going to kind of go over the kinematics problems here that I did in class. So this is kind of what I'm doing in class. What I really am dealing with is the fact that in problem number 13 we have the airplane that we did in the notes exactly the same, except that now it's moving at twice the velocity. So it's moving at 230 meters per second instead of the 115, but still being dropped from the same altitude. So my picture over here is trying to show that. And just like I mentioned in class, it's really kind of neat that if the airplane moves at the same velocity all the time, then the package would be right underneath that. And really all it's doing is it's following this nice little parabolic motion until smack it goes into the ground. But it's always right underneath the plane at each one of those moments in time as it builds up some velocity. Now, all of these set of problems are horizontal projectile problems. So one of the things that I think is kind of nice is with horizontal projectile problems, all of your motion is in the Vx direction and there's no initial vertical velocity. So in other words, the vertical velocity, the VIY, is going to be 0. And the reason why that is the case is because you are only moving horizontally. So if you look at this picture right here, we don't actually have a little VIY. Later on, we actually do have a VY, and then a little bit later we have another VY. So it gets bigger and bigger, but it starts off with none. What that does is this equation, our y equal VIT minus 1/2 GT squared, this was originally written like this, and then what I did is I put a little y subscript on there. Since VIY is 0, this part of it disappears, and you're just left with y equals minus 1/2 GT squared. And if I take that and I solve it for t, I can multiply by -2. So by 1/2, I can divide by g, and then I square root to get t. This is another equation I would suggest that you put onto your equation sheets, because this works as long as VIY is 0. So if your initial vertical velocity is 0, you should be able to use this to your advantage. But it only works if the initial vertical velocity is 0. So if the initial vertical velocity is 0, we can do that. What that tells me then is it doesn't matter what the initial horizontal velocity is, because this is a Vx. This 230 meters per second. That does not affect any of the vertical fall. All we have to do is plug in time, square root of -2 times the -1050. Why is it negative? Because it's falling 10,000 or 1,050 meters divided by 9.8. And what we get is our time is still 14.6 seconds. The same thing we got when we actually did this before in the video notes. So very key idea. I think the next part is just to kind of continue to make your way through here. But one of the things I was trying to point out in class is as you look at all of these different problems, something is moving horizontally. Horizontal cliff for the golf ball. Criminal is running horizontally. The pitcher throws it horizontally. The diver runs horizontally. Suppose the water at the top has a horizontal speed. A child is operating, they accidentally steer off the edge. What's the car's speed? This one doesn't actually say anything about a horizontal, but it accidentally steers off the edge of this dock, so we're assuming it's horizontal. Horizontal. The marble is thrown horizontally. The eagle is flying horizontally. The baseball player bunts so that it acquires a horizontal initial velocity parallel to the ground. That's horizontal. So all of these are horizontal. That means VIY is going to be 0 for all of these, and we can use that to our advantage. The next one I think is really nice to do is problem number 21. So I'm going to take that, and I'm running out of space here, so I'm going to jump to a new page. I think it's very useful in 21 to actually make a picture. So that's what I'm going to do here. There's my water, there's my lake. So the idea is I have my golf ball, put some dimples on it. It's moving horizontally because it's coming off this horizontal cliff, so that Vx is the 11.4 meters per second. So when they say that the golf ball is rolling off this cliff at an initial speed of 11.4 meters per second, that's really saying Vx. This golf ball is going to go flying through the air, hit the water, splash. It's now in the water. Splash. The other bit of information they tell me is how far it falls vertically. So from here down to the water was 15.5 meters. This was in the problem, that it falls a vertical distance of 15.5 meters. Now, the reason why they use the word distance and not displacement is you have to interpret that. So this would be a y because it's going vertically, but we have to put this in as negative because it's going down, so it's falling that. What I don't know is I don't know how far this thing is moving horizontally. So I don't know this. I don't have x. Because of that, please, 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 for part A, I get so many people that want to use this equation, but we don't have x. You can't do that. Do not put in the y for x. So we can't use that equation. Instead, what I would use is the equation we just came up with. Minus 2 times y over g. It's a great equation because this is only going horizontally. The initial vertical velocity is 0 for this setup. All of the motion is in the horizontal direction. So I would be taking minus 2 times your negative 15.5 over 9.8. Ka-chunk that out. You find out that this thing is going or falling for 1.78 seconds. So just to help you out. Yeah. Now the second part is going to be the more important part. Part B. Part B wants to know what is the speed of the ball just before it strikes the water. And it says VF. So as I get ready to do this, what most people do is they say, okay, I'm looking for an equation that has VF in it. I don't think it's just simple saying that this is my velocity. I don't think it's that simple. It's got to be a little more complicated than that. So what do I have that has VF in it? I have an equation that looks like this from chapter 2. So maybe it's this equation. But in chapter 3, we add these little y subscripts on here. And yes, we could use this, and we are going to be using this. Or, if you didn't trust your time, we do also have that VF squared equals VI squared minus 2GY. And again, I put little y subscripts on my velocities to indicate that they're vertical. Either one of these, both of these should give us the same answer. The key idea, though, is we know our VIY is 0, so this part's going to be 0. So I'm going to go ahead and use this one. I feel confident in my time. So it's 0 minus 9.8 times this 1.78 seconds. So VFY is negative 17.4 meters per second. And you can double check it, even if I do it with this one. VFY squared would equal 0 squared minus 2 times 9.8 times a negative 15.5. This will actually give you the same thing. VFY would be 17.4 meters per second. Now the thing to watch out for is notice that it's a squared up here. And so a lot of people put that as positive, but we saw this with the Gwen Stacy problem. She was thrown downward. She fell from the bridge down into the water. Everything is downward. When you are taking a square root, remember, technically there are two possible answers, positive or negative. And so I get people who are like, oh, it's positive or negative. But in this case, we know it's actually the negative that we want because it's going down. Most people stop there. They're like, ta-da, done. ready to go, print, send it to Mr. Hinnon. But if I do that, you're going to miss points. And here is the reason why. If I actually look at this golf ball, it traveled through the air, and eventually it hits the water. So the golf ball is now right here. The key thing as this golf ball travels through the air, just like our package in problem number 13, it still is moving horizontally at 11.4 meters per second. So even when it strikes the water, right as it strikes the water, it's still moving forward at 11.4 meters per second. What I have found here is that it also now is moving vertically downward at negative 17.4 meters per second. Technically, neither one of those is the answer the book actually wants. What they really want is, since the ball is hitting diagonally here, they want this. This is what they mean by VF. They want to know how fast is the ball going diagonally, following that parabolic path. How do I do that? Well, guess what? Remember how we said that chapter 3 builds on chapter 2 and chapter 2 built on chapter 1? Technically, physics builds on itself. That's exactly what we've got going on here. What we're going to, in essence, do is we need to take, oops, that's not going to work. We need to take this little velocity and move it over. So I'm going to take this velocity right here, and I'm going to put it right on this side. So VFY is going to go right here. Guess what? Horizontal and vertical are perpendicular. What I've got is a nice triangle. And so I actually pointed this out in class, that we should add some equations besides equations like this and this and this to our equation sheet. We need to add Pythagorean theorem. But we're going to write it a little bit different. Pythagorean theorem. I want the hypotenuse. Normally we say a squared plus b squared equals c squared. But now a is vx. So vx squared plus b is your vfy squared. And your hypotenuse c is vf. So add this to your equation sheet. It could be f's here, so these could all be finals, or we're going to actually find out these could all be initials. So notice that this is just plain VF. It doesn't have an X or a Y because it's a diagonal, and that's what we're going to actually use. So to find this, we're going to take 11.4 squared plus a negative 17.4 squared should give you VF squared. Square them, add them, square root it, and what you should find out is that VF itself is 20.8 meters per second. Do I need some kind of negative sign on there to indicate that it's going downward? And actually with diagonals, we don't do that. And the reason why we don't do that is because we are actually talking about a decline in the measurement. So it's positive in the horizontal direction, but it's negative in the vertical direction. So we leave it as a magnitude, how fast it's moving. If I did want a direction, what I would now have to do is give me angles. So I would have to find this angle right here. What is theta? So I'm going to add one other thing to our equation sheet. I often think that it's useful to take the tangent and use TOA from SOHCAHTOA and say the tangent of this angle of declination would be my VFY over my VX. VFY over VX. So I would add this to my equation sheet as well. And what that does is now we've got new ones. Like I said, technically these are all F's. We're going to find out a little bit later in this chapter. These could also be initials. So initial velocities, just same with this. These could be initial velocities as we are launching stuff, but since in this case all of our motion is initially horizontal, we don't have to worry about it. So that's a little bit of help on the problems. This is about as far as I went in class. I pointed out a couple of things, and then we went some more. So this is a little bit of help that I'm sending out to everybody, and I hope you enjoyed. Thanks.